что можно начинать, да? Okay, today our first goal and our main goal will be to discuss two Banach algebras associated to locally compact groups. The first Banach algebra is L1 of G. It consists of integrable functions with respect to the higher measure. And the second one the second algebra is bigger, and it consists of complex Radon measures on our group. Well, let's start with L1 of G. L1 of G. So we take a locally compact group, G, and from the very beginning we assume that it is second countable. Second countable locally compact group. That is, we assume that its topology has a countable base. There is a countable base for the topology on G. We take a higher measure. Mu is a higher measure on G. And let's recall from the previous lecture that in this case, the product measure, mu tensor mu, is a higher measure on the product, G cross G. Here is the point where we use the assumption that G is second countable. Because if G is not second countable, then in general, this measure is defined, is not defined on all Borel sets. It is defined only on the smaller sigma algebra generated by Borel rectangles, that is, by products of two Borel sets. And in general, this sigma algebra is smaller than the sigma algebra of Borel sets. But if G is second countable, then everything is okay. So the Borel sigma algebra is generated by Borel rectangles. This measure is defined everywhere, and it is left invariant. So it is a higher measure on the product. Actually, there is a certain way around this problem, and we can modify the definition of this measure in the general case, that is, in the case where G is not second countable, and to define it eventually on the Borel sigma algebra. But I'd like to avoid some measure theoretic technicalities just to save time. So we assume that G is second countable. Okay, so we denote by M mu the sigma algebra of all mu measurable sets. A is mu measurable. So let's recall that it's a standard fact from measure theory that this sigma algebra consists of all sets of the form B union with N, where B is a Borel subset of G, and nu is a mu null set, which means that it is contained in a Borel set of measure 0. Nu is contained in, say, C for some Borel set C of measure 0. So a mu is sometimes called the completion of the Borel sigma algebra of the sigma algebra of Borel subsets of G, and its advantage is that every subset of a set of measure 0 in a mu is also measurable, and its measure is 0. So this is useful sigma algebra. When we speak of integration, it is sometimes it's often convenient to enlarge our original sigma algebra of Borel sets to the sigma algebra of measurable sets. So we have the following lemma, which was already stated at the previous lecture. Suppose we have two measurable functions, f and g, on our group. I mean measurable with respect to the complete sigma algebra of measurable sets. And we define a function big F on the product of G by itself by the following formula. so the reason for introducing this function is that we will need it when we define convolution. So if you remember the formula for convolution of two functions, for example, on the circle, then this formula involves exactly this function. So I claim that f is measurable with respect to this sigma algebra of measurable sets on the product. So after we prove this lemma, we will be able to use this fact to define convolution of two integrable functions. To prove the lemma, let's decompose the function f as follows. So the first map will be, as denoted by alpha. It acts from G cross G to itself, and it takes each pair yx to y inverse x. Next, we apply the product, the direct product of f and g. So it takes G cross G to C cross C, and then we compose with the usual multiplication on the complex numbers. Clearly, the composition is just our map F. This is F. So what can we say about these three maps? Well, the multiplication is, of course, continuous on the complex numbers, so it is a Borel map. Is continuous, and hence it is a Borel map in the sense that the preimage of a Borel set is Borel. As for this arrow f cross g, it's almost immediate from the measurability of f and g that this function is also measurable with respect to the completed sigma algebra of subsets of the product. This function is measurable. Well, indeed, it suffices to observe that the preimage of every Borel rectangle is measurable. But if we take a Borel rectangle here, the preimage will be a product of two sets of this form, because f and g are measurable. And clearly, the product of two sets of this form is a set of the same form in the product. So this function is measurable. As for alpha, we can only say that alpha is clearly a homeomorphism. Is a homeomorphism of G cross G to itself. And so it is a Borel map. But this is not exactly what we want. I claim that alpha is measurable with respect to the completed sigma algebra of the product. That is, the preimage under alpha of a set in this sigma algebra sits in the same sigma algebra. Why is it so? Well, indeed, if we take continuous compactly supported function phi on the product, let's calculate the integral of the following function with respect to the product measure. So we apply the Fubini theorem, and we replace this by an iterated integral. So the inner integral will be taken with respect to x, and then with respect to y. But mu is left invariant, so when we integrate with respect to x, we can replace actually so we can replace this guy just by x, because the measure is left invariant. So this is the integral of phi yx. That is just the integral of phi with respect to the product measure, again by Fubini's theorem. And so by looking at this equality, we deduce that alpha is measure preserving, this is just the composition of phi and alpha, and this is just phi. So this implies that alpha is measure preserving. And therefore, the preimage of every null set is a null set. Every not with respect to mu, but with respect to the product measure for every null set n in the product, the preimage is also a null set. And now by looking at the this characterization of measurable sets, so where every measurable set is a union of a Borel set and a null set. So alpha is a Borel map, so the preimage of a Borel set is a Borel set. Now we see that the preimage of a null set is a null set, and as a result we deduce that alpha is measurable with respect to the completed sigma algebra. Which proves the claim. And essentially this completes the proof of our result, because now we simply look at this picture and we observe that f is the composition of three arrows, each of which is measurable with respect to the suitable sigma algebras. So the preimage of Borel set here is Borel here, the preimage of a Borel set here is measurable here, and the preimage of a measurable set here is measurable here. That is, f is measurable. Okay, so this completes the proof of our technical lemma. And so we can now define a convolution of two functions on G. Suppose we have two measurable functions f and g. We define the convolution of f and g is to be a function given by the well-known formula, which we are already familiar with from harmonic analysis on the circle and on the real line. So it is given by the following formula: f of y, g of y inverse x, and we integrate with respect to y. Of course, I don't claim that this is defined everywhere. If we assume that f and g are just measurable, we know nothing about this integral. But as usual, we follow the convention that the convolution is defined at those points of the group where the integral exists. This integral exists. Okay. Well, let's make a short break now. I'll try to find some chalk, and then we continue. Okay, so in the general case, this integral, in the general case, this function is defined only at those points where the integral exists. But now we are interested in the case where f and g are integrable. And it turns out that if they are integrable, then the convolution exists almost everywhere. It is defined almost everywhere. And moreover, have the following result. The theorem. First, if f and g are integrable, then the convolution is defined almost everywhere. Moreover, it is integrable. And the L1 norm of the convolution is less than or equal to the product of the norms of f and g. And this operation makes L1 of g into a Banach algebra. Part 2, L1 of g, equipped with the convolution multiplication, is a Banach algebra. Moreover, it is a Banach star algebra with respect to the involution defined as follows. The function f star of x is f of x inverse, complex conjugate, multiplied by the modular character delta of x inverse. Of course, this star here and the star here, they have different meanings. So this is the convolution of two functions, and this is the involution of a single function. But I hope this is not a serious problem. Well, to prove the first part, we consider a function big F defined in the previous lemma. F of yx is the following function. And by lemma, this function is measurable. So let's first of all, let's prove that this function, or more exactly, its absolute value, is integrable over the product. Well, this function is non-negative. So the absolute value of f is non-negative. So in any case, the integral is defined. The integral is defined for every non-negative measurable functions, for every non-negative measurable function, but sometimes it is equal to infinity, to plus infinity. And if it is finite, then the function is integrable. So let's calculate this integral. We use here the so-called Tonelli theorem, which is kind of inverse to the Fubini theorem, and which tells us that if if we deal with an arbitrary measurable function, non-negative measurable function, then we can interchange the integrals. So we can replace in particular, we can replace the integral over the product measure by the iterated integral. In the sense that this one exists if and only if this one exists, and if in this case they are the same. Okay, so what's that? This is the integral of the absolute value of f of y, g of y inverse x, d mu of x, d mu of y. So first we integrate with respect to x, and here again we use the left invariance of the measure. And by left invariance, we replace here y inverse x just by x. So we get f of y, g of x, d mu of x, d mu of y. And now when we integrate with respect to x, we get exactly the L1 norm of g. Then we integrate with respect to y, we get the L1 norm of f. So the result is just the product of two norms, the norm of f and the norm of g. And this is finite. So as a result, the absolute value of f is integrable. This function is integrable. and hence f is also integrable. So is f. Again, here we use the assumption that it is measurable, of course. Not the assumption, but the fact that it is measurable by lemma. So f is integrable. And now we apply the Fubini theorem, which tells us in particular that if we fix one of the variables, then the resulting function of one variable will be integrable almost everywhere for almost all elements in the group. This is by Fubini's theorem. The function, let's denote it like this, but it's clear what I mean. So I fix x and consider this function as a function of the argument y. So it is integrable for almost all little x. And this means that the convolution is defined almost everywhere. That is, the convolution of f in G is defined almost everywhere. And moreover, again, the same theorem, Fubini's theorem, tells us that if we take every point x to the integral of this function with respect to y, we get something integrable. Moreover, the function which takes x to the integral of this function is integrable. So in other words, the convolution is integrable. The convolution of f and g is integrable. And finally, we want to evaluate the norm, the L1 norm of this function. So this is the integral of the absolute value of the convolution evaluated at x. So clearly, if we move the absolute value sign inside the integral, we get something bigger. But what we get is exactly the integral of big F over the product. Again, by Fubini's theorem, we replace the iterated integral by the integral over the product. But we already know, look here, we already know that this integral is exactly the product of two norms of f, of little f and little g. And that's it. So this completes the proof of part 1. Part 2 is actually a routine calculation. So this is a simple exercise for you. So formally, we have to prove that the convolution is associative. Again, this is some calculation involving Fubini's theorem. And that this formula indeed defines an involution on this algebra. It is isometric by the usual property of the modular character, which was discussed in the previous lecture. And it is an algebra anti-homomorphism. So it is an involution. Which one? This one. We just move the absolute value from here to here. And this will be just the absolute value of big F. Let's look at some more properties of this algebra. This is an exercise for you. First of all, I claim that this algebra is commutative. L1 of G is commutative if and only if G is commutative. Well, the right to left implication is again absolutely automatic. If you assume that G is commutative, then and calculate a convolution of f and g and of g of f, they will be the same. This is very easy. A more interesting exercise is to show that the commutativity of L1 of g implies the commutativity of g. And the second part claims that in general the algebra L1 of g is not unital. More exactly, it is unital if and only if g is discrete. And in this case, if g is discrete, then L1 of g is nothing but little L1 of g, the set of all summable series over g, and the identity of g is the Dirac measure, or exactly the Dirac function concentrated at the identity. Delta E is the identity of L1 of g. And finally, well, it is a Banach star algebra, so the natural question is it a C-star algebra? And the answer is no. It is not a C-star algebra, except for the trivial case where G is trivial. It is not a C-star algebra unless G consists of a single element. So this the L1 norm doesn't satisfy the C-star axiom. Moreover, it turns out that, well, if G is finite, clearly if G is finite, then L1 of G, well, not absolutely clear, but it's rather easy to show that if G is finite, then L1 of G is finite dimensional, so it is isomorphic to a C-star algebra. But if G is infinite, then this is not the case. So we will be able to prove this shortly. Well, not shortly, but by the end of the course, that if G is infinite, then L1 of G is never isomorphic to a C-star algebra. So we cannot replace the original norm by an equivalent one, which satisfies the C-star axiom. Okay. So our next goal will be to discuss a bigger algebra whose elements are complex Radon measures on the group. But before defining this algebra, let's recall some basic facts on complex measures. Probably you know some of these facts from a measure theory course, but maybe some of them will be new. So first of all, we take a set, X is an arbitrary set, and a sigma algebra A of subsets of A. And by definition, a complex measure on A is basically a sigma additive measure with values in the complex numbers. But this is a map, mu, from A to the complex numbers, such that for every sequence of disjoint sets, A1, A2, and so on, in our sigma algebra, such that they are disjoint, we have the following equality. The measure of their union is equal to the sum of their measures. So exactly the same definition as the usual definition of a positive measure, but now the measure is complex valued. Two little remarks concerning the definition. First of all, so here we require the series to be convergent. So we assume that the series is convergent. But what I want to stress is that it is absolutely convergent. That's denoted by star. So series star converges absolutely. Why is it so? Well, the left-hand side of the equality doesn't depend on the order of the sets. So as a result, we see that this series converges independently of the order of the summands. And it's well known that in this case, the series converges absolutely. And second, I'd like to stress that just by the very definition, the complex measure is not allowed to take the value plus infinity. So in other words, complex measures don't generalize positive measures, because when we speak of positive measures, a positive measure is allowed to be infinite at some sets. But a complex measure is not allowed to be infinite. In some senses, it's always finite, but sometimes it is complex. To work with complex measures, it's convenient to associate to a complex measure a certain positive measure, which is called the variation of mu. By definition, the variation of a complex measure mu is a function denoted like this. It is defined on the same sigma algebra. It is positive. And is given by the following formula. If A is a set in our sigma algebra, then we consider all finite representations of our set A in the following form. Is this joint union of finitely many sets in our sigma algebra. For each such partition, we take the sum of the measures of AI. We take the absolute value here. And finally, we take the supremum over all partitions. And this is the definition of the variation of mu. So if we look at this formula, it's not clear at all why this should be finite. That's why I put the square bracket here. So maybe it is infinite sometimes. But it turns out that it is not. So we have two useful facts. First of all, I claim that the variation of a complex measure is a measure, a positive measure. Of course, sigma additive. This is rather easy and straightforward. And what is not entirely straightforward is that this measure is also always finite. This is finite for every A. It's also clear from the definition, here's the definition. It's also clear from the definition that this measure is the smallest among all possible positive measures which dominate mu in the following sense. So let's observe that if mu is a positive measure, possibly infinite, on A, such that for every set in our sigma algebra we have the following inequality. So the absolute value of mu of A is less than or equal to nu of A. Then the same is true for the variation of mu. The variation of mu is less than or equal to nu. So the variation of mu is the smallest positive measure which dominates mu. So this justifies its definition. If our measure mu is real valued, then there is a useful fact which reduces real valued measures to positive measures. And this is the so-called Jordan decomposition of a real measure suppose that mu is a measure from A, and suppose it is real valued. Then there exists a unique pair consisting of two positive measures, mu plus and mu minus, of positive measures on A, such that mu is their difference, and such that they are mutually singular. In the sense, which means that they live on disjoint sets. There is a partition of X into two disjoint sets, such that mu minus vanishes on the first set and mu plus vanishes on the second one. So they are mutually singular. And this formula is called the Jordan decomposition of mu. Moreover, in this case, the variation of mu is just the sum of these two measures, mu plus and mu minus. So by using this decomposition, we can now easily explain how to integrate with respect to the real valued measures and then with respect to the complex measures. So we give the following definition. Suppose that f is a measurable function measurable with respect to our sigma algebra A, the preimage of a Borel set sits in A, and suppose that mu is a real measure on A, we say that f is integrable, mu integrable, by definition, if f is integrable with respect to mu plus and mu minus. Mu plus integrable and mu minus integrable. And in this case, we define the integral. We define the integral of f with respect to mu to be the difference of two integrals with respect to mu plus and with respect to mu minus, which is quite natural. So this explains how to integrate with respect to a real measure. And now to integrate with respect to a complex measure, we simply consider the real and the imaginary part of mu. So our next definition, suppose that now that mu is a complex measure on A. Let's decompose it into the following combination, mu1 plus I mu2, where mu1 and mu2 are real. So in other words, mu1 and mu2 are just the real and the imaginary part of mu. And we say that f is mu integrable if, by definition, if f is mu1 integrable and mu2 integrable. And in this case, we define the integral of f with respect to mu to be the following combination. F with respect to mu1 plus f with respect to mu2, which is also quite natural. Oh, I forgot. No, I didn't forget. I times the integral of f with respect to mu2. Okay, so this is the integration rule for functions with respect to complex measures. By the way, the integrability of f is actually equivalent to the integrability with respect to the variation of mu. I claim that f is mu integrable if and only if it is integrable with respect to the variation of mu, this is a useful exercise. And moreover, we have the following inequality. If we integrate with respect to mu and take the absolute value, this is less than or equal to the integral of the absolute value of f with respect to the variation of mu. Okay. So far X was an arbitrary set. Let's now suppose that X is a locally compact Hausdorff topological space. Let now X be a locally compact Hausdorff topological space. Again, it's natural to consider those complex measures on X which are compatible with the topology. So by definition, we say that a complex Borel measure mu on X is a Radon measure. A Radon measure if its variation is a Radon measure. In the usual sense. The set of all complex Radon measures on X will be denoted by M of X. This is a standard notation in measure theory and in harmonic analysis. So this is the set of all complex Radon measures on X. Actually, this is not just a set, this is Banach space. The vector space structure is pointwise, so it's clear that a linear combination of two, it's almost clear, it's a simple exercise in measure theory, that a linear combination of two complex Radon measures is again a Radon measure. And moreover, it's an exercise that M of X is a Banach space with respect to the norm given by the following formula. The norm of mu is, so we take the variation of mu and evaluate it at the whole space X. And we get a Banach space. The elements of the space can be conveniently interpreted as linear functionals. So let's introduce some more notation. Let's denote by B of X the space of all bounded Borel functions on X. Bounded Borel functions on X. And of course, this is also a Banach space under the uniform norm. The norm of F is just the supremum of the absolute value of X. And it's a standard fact that this is a Banach space. So now we can integrate functions in this space with respect to complex Radon measures by using this rule and this rule. So if mu is a complex Radon measure, first of all, if mu is real, then mu plus and mu minus are finite real measures. So both these numbers are well defined. So this is well defined. And if mu is a complex measure, then for the same reason, this is well defined, this is well defined. So F is integrable. And as a result, we get the following map. Again, this is a little exercise. No, actually, it seems to me that there is nothing to prove here. let's just observe. Let's just observe that we have a map. We have a linear map from the space of complex Radon measures to the space of bounded linear functionals on B of x, which takes every complex measure mu to the functional I mu given by integration with respect to mu. In general, if x is big enough, then this map is not surjective. There are many other linear functionals on B of x, some of which are quite exotic. But if we restrict this functional to the space C0 of x of continuous and vanishing at infinity functions, then we get an isometric isomorphism. And this is a famous theorem, which is usually attributed to Riis, Markov, and Kakutani. And it tells us that the map from M of x to the dual of C0 of x, which takes every mu to I mu, is an isometric isomorphism of Banach spaces. Well, you may have noticed that this result is very close to another theorem also due to Riis, Markov, and Kakutani, which was discussed some time ago, and which is about positive functionals on the space of continuous compactly supported functions. So positive functionals on the space of continuous compactly supported functions are in a one-to-one correspondence with positive Radon measures. So these results are very closely related, but formally none of them is generalization of another one. So this theorem doesn't generalize the fact about positive functionals because they are defined on another space, on compactly supported functions, and they are given by possibly infinite measures, positive but possibly infinite measures. And here the measures are finite, but they are complex. So this result is not more general than the previous one and the other way around. But anyway, they're closely related. So that's the reason why they are attributed to the same people. Actually, this one can be deduced from that one and the other way around. Okay, now a few words about products of Radon measures, products of complex Radon measures. A definition. Suppose we have two locally compact spaces, x and y, locally compact Hausdorff topological spaces. And suppose that mu and u are complex Radon measures on x and y respectively. If they are real, this is the first part of the definition. If mu and u are real, then we can define their product, the product measure, mu tensor nu, by using the Jordan decompositions of mu and u. So mu is mu1 minus mu2, mu plus minus mu minus. Nu is also the difference of two positive measures. So these are the Jordan decompositions. And just by definition, we'll let their tensor, their product be equal to the following measure on the product: mu plus tensor nu plus minus mu plus tensor nu minus minus mu minus tensor nu plus plus mu minus tensor nu minus, which looks quite natural. And in the general case, if they are complex measures, then we again reduce everything to real measures by taking the real and imaginary parts. In the general case, we define the product measure as follows. We decompose mu1 and mu2 as follows, where all these four measures are real. And define the product measure as follows. This is mu1 plus tensor nu1 minus mu2 tensor nu2 plus I times mu2 tensor nu1 plus mu1 tensor nu2. And that's it. So this defines the product measure for any two complex measures mu and u. Okay, now we are ready to define the measure algebra of a locally compact group. Measure algebra. So again, we take a second countable locally compact group G. Second countable locally compact group. And we introduce the following notation. We denote by delta map from C0 of G to the space of continuous bounded functions on the product G cross G by the following formula. So the function delta f evaluated at x and y is f evaluated at x, y. So clearly this is a linear map. Actually, it is an isometry. The supremum norm of this function is easily seen to be equal to the supremum norm of f. Let's call it the commultiplication on C0 of G. I put the quotation marks here because this map is not a commultiplication in the purely algebraic sense. Moreover, the resulting function is not in C0. It is continuous and bounded, but in general, this function doesn't vanish at infinity. Generalized commultiplication of this kind naturally appear in the theory of multiplier Hopf algebras and in the theory of locally compact quantum groups. But this is not the subject of our course. Anyway, this concrete map will be quite useful because it enables us to define a multiplication on the measures on the space M of G. By definition, if we have two complex Radon measures mu and u, we define their convolution. The convolution of mu and nu is again a complex Radon measure on G given by the following formula. So if we interpret this measure as a linear functional, so we use the Rees-Markov-Kakutani theorem, then this linear functional acts on a continuous C0 function f in exactly the same way as the product measure u tensor nu acts on delta f for all f in C0 of G, where the angle brackets denote just the integration. This is just a notation. So this is well defined. Delta f is not in C0, but this is not a problem. It is, nevertheless, this is a bounded continuous function, and of course we can integrate a continuous bounded function with respect to this measure. So we get now an operation on a space of measures, and I claim that M of G becomes a Banach algebra. M of G is equipped with the convolution, multiplication, is a Banach algebra, and moreover it is a Banach star algebra with respect to the involution given by the following formula. Mu star of B is mu of B inverse, and we take the complex conjugate here. And it is called the measure algebra of G. The measure algebra of G. An equivalent way of writing the involution on the measure algebra is as follows. The measure mu star evaluated at C0 function f. So what is this? We first take S of f, where S of f is, as usual, f evaluated at x inverse. Take the complex conjugation, then integrate with respect to mu, and finally again take the complex conjugate here. The proof is quite straightforward, and this is an exercise for you. In fact, everything is already reduced to the assumption that, to the fact that the multiplication on G is associative. So this is quite straightforward. By the way, let me remark that explicitly the convolution can be written as follows. The integral of f with respect to the convolution of mu and nu is the integral of f of xy d mu of x d mu of y. This is just an explicit way for writing this formula. But by using this formula, we can easily show that the convolution of measures is associative. So it's a Banach star algebra. When is it commutative? Here the answer is exactly the same as in the case of L1 of G. M of G is commutative even only if G is commutative. A nice property of the measure algebra is that in contrast to the algebra L1 of G, the measure algebra always contains the algebraic group algebra of G. So we have the following proposition. For every point x in our group, let's consider the corresponding Dirac measure. Let delta x denote the Dirac measure concentrated at x. There is a little abuse of notation here. So before by delta x we denoted the function, which is 1 at x and 0 elsewhere. But the same symbol is traditionally used to denote the respective Dirac measure, and this is quite standard. So I hope this is there is no problem here. So I claim that for every f for every measure, for every complex measure on G, the convolution of delta x and mu is nothing but the left translate of mu, Lx mu, which was defined some time ago. And the right convolution of m and delta x is the right translate of mu by x inverse. And finally, if we take the convolution of two Dirac measures, delta x and delta y, we get the Dirac measure delta xy. So as a result, this formula implies that, well, let me write it here. So we have a map from the algebraic group algebra of G as denoted by alpha to the measure algebra M of G, which takes every element x of G to the Dirac measure delta x. So I claim that this is an injective algebra homomorphism. So the algebraic group algebra becomes a part of the measure algebra. Usually it is not surjective. It isn't surjective, or equivalent, it is an isomorphism if and only if G is finite. Alpha is an isomorphism if and only if G is finite. Again, the proof is quite straightforward. I mean, the formulas for the convolution with delta functions is so this readily follows from the definitions, from the definition of mu star nu. Well, and the fact that this is not surjective is also a useful exercise. Actually, we can extend this map to a bigger algebra. This is another exercise. Alpha extends to an homomorphism, which is moreover isometric, to an isometric homomorphism, as denoted now by delta, by beta. From the algebra little one of G, which consists of summable series over G, to the measure algebra. And again, it's uniquely determined by the following rule. And it is isometric. So if we take a measure concentrated in countably many points with suitable weights, then the variation of the respective measure is exactly the sum of the absolute value of the weights. So this is an isometry. And this map is, again, in general, it is not surjective. More exactly, it is an isomorphism if and only if G is discrete. If and only if G is discrete. Well, okay, let's now compare the Banach algebras L1 of G and M of G. So of course you notice that we use the word convolution in two differing meanings. So we have a convolution of integrable functions, and we have convolution of measures. Of course, these two types of convolution are closely related, so let's now explain what the relation is. So let's introduce some notation. From now on, mu denotes a Haar measure on G. By default, mu is the left Haar measure on G. And for every integrable function, f in L1 of G, again, I'd like to stress then when I write L1 of G, I mean the L1 algebra with L1 space with respect to the Haar measure, of course. By the way, let me also remark that the definition of L1 of G depends on the Haar measure. If we choose another Haar measure, which is of course, defined uniquely up to a positive constant, but formally the norm on the space will not be the same. It will be multiplied by a constant. But the measure algebra doesn't depend on the choice of a higher measure. The measure algebra consists of all complex Radon measures, and the definition of the measure algebra doesn't involve the higher measure at all. That's the difference. This algebra, the definition of this algebra involves the higher measure. So now for every integrable function f, we define a measure. Mm-hmm. Ну да, ну потому что у нас есть система Рейса-Маркова Кокутани, что мы должны, это же у нас функционал, мы его должны на функциях из ценой определить. Вот так определяем. То, что вот мы прямо по определению. Тут мы пользуемся, конечно, теоремой Рейса-Маркова Кокутани.
А если просто вот эту меру сверху посчитать его на множестве а, там же вот f...
Да, можно.
Будет... Нет индикаторов, но было какое-то приближение.
Ну, в каком смысле, да. Угу. Можно. Мы уже предположили, что группа со счетной базой, так что тут, в общем, проблем опять-таки не возникает с приближением борельских множеств посредством компактных изнутри и открытых снаружи. Ну, вот, поэтому все хорошо будет. Так что можно и на множествах написать, будет просто немножко корявая формула, а это такая вот более уже. Okay, so we take now an integrable function f and we define a Radon measure, a complex Radon measure fu on G as follows. So since this is a functional, we must explain what is f mu evaluated at G, where G is a C0 function on G. And by definition, this is mu evaluated at the product Fg. Of course, Fg is no longer a function in C0, but there is no problem because f is integrable, so Fg is also integrable. Okay, it's a simple exercise to show that we can explicitly define this measure on all Borel sets by the following formula. For every Borel set B in G. And we have the following result. The following result, proposition. Consider the following map, that's denoted by I, from L1 of G to M of G, which takes every function little f to f mu. So f mu is the measure given by this formula. This is the measure which is absolutely continuous with respect to the higher measure with density f. So I claim that this map is an isometric star homomorphism of Banach algebras. So it preserves the norm, and it preserves the product, the convolution, and it preserves the star, preserves the involution on L1 of G. So L1 of G essentially becomes a closed subalgebra in M of G. So we might identify L1 of G with its image under this map. So it becomes a closed subalgebra, but actually we can say more. So let's identify L1 of G with the respective subset of absolutely continuous measures in M of G. So I claim that this is not just a closed subalgebra, but actually it is a closed two-sided ideal. L1 of G is a closed two-sided ideal of M of G. And we have the following formulas for every integrable function f. and for every complex Radon measure nu on G, the convolution of nu and f, so it sits in L1 of G, and it is given by the following formula. F of y inverse x d nu of y. So this generalizes the usual formula for convolution of two functions, where in the case where nu also belongs to L1 of G, we get the usual convolution formula of two functions. But it extends to measures in this way. And if we want to convolve on the right, then we get something slightly more difficult. We get the integral over G of x y inverse delta of y inverse d nu of y, where again delta is the modular character. Again, the proof is quite straightforward. So I'll leave this as an exercise for you. Basically, we to prove all these results, we do some little calculations which involve the definition of convolution of functions, of convolution of measures, and essentially that's all. So just calculate. So we have to prove that this map preserves the convolution, preserves the norm. The only not entirely computational part of this result is to prove that this map preserves the norm, that it is isometric. The hint is to use this formula. So by using this formula, first of all, to prove that it is isometric, it suffices to prove that it preserves the norm of characteristic functions of Borel sets, because the characteristic functions of Borel sets are total. They are total in L1 of G. So basically, everything reduces to characteristic function of Borel sets, and for them, the fact that this map is isometric can be reduced to this formula.
What's the norm on M of G?
The norm on M of G, this is not an electronic blackboard, so let me write this once again. The norm on M of G is given by the following formula. We take the variation of mu and evaluate at G. So this is a norm on M of G. And the fact that it is an algebra homomorphism, that it preserves the involution, and that L1 of G is a two-sided ideal, this is a straightforward calculation. I see it's time to finish. Okay, so that's all for today. At the next lecture, we discuss a useful property of L1 of G. The property is that this algebra, in spite of the fact that it is not unital in general, it is approximately unital in a suitable sense. So in general, we see that we have two natural Banach algebras associated to a locally compact group, L1 of G and M of G. M of G has the advantage of being unital, and it contains the algebraic group algebra. So one may think that M of G is better in a sense than L1 of G. But the truth is that M of G is very big, and sometimes it demonstrates a rather wild behavior. So L1 of G is much better behaved than M of G. But it is not unital. And at the next lecture, we discuss the notion of an approximate identity in the Banach algebra. And we will see that L1 of G has an approximate identity. So this is a suitable generalized sequence, or more exactly a net, which replaces the identity in this algebra. So there is no identity, but there is an approximate identity. Okay, thank you. That's all for today.